So I will talk about social network analysis, algorithms and applications. So, um, so th- oh, okay, okay. So there are many places where graph analytics is being applied. So I thought that because social networks are one of the important applications of graph analytics, so I'll talk about social networks. Um, Okay. So there are some interesting applications of network theory. So for example, many of us know about this World Wide Web and hyperlink structure. Um, um, okay. Oh, okay. Um, there are many places where social network analysis is being applied. So one is the World Wide Web and hyperlink structure, then the internet and router connectivity, collaboration among movie actors, scientists and mathematicians, romantic relationships, cellular networks in biology, food webs, and there are many such applications. Now, so this graph analytics is not a new thing. I mean, already we know many of these things from graph theory. Um, okay, but the applications that are coming out to be they are quite novel here. Um, so I'll give some of the examples where graph analytics are being applied. For examples, if you want to find out what are the important pages in in web pages, like then you can use various techniques like page ranks or authorities and hubs. Then if you want to find discover communities in a graph, then you can use various community detection algorithms. Also, you can use analyze trust, like how trust propagates in a network, and how this can be used to fight spam in email or web page ranking. So how do you model a social network? So in many cases, what happens is that you have these the elements of social networks are so the elements, the individual nodes are the people, and then there is a relation between them. So the difference between normal type of analytics and graph analytics is that so in normal analytics you have say numbers or text as inputs, and then you want to do find some kind of insights. But whereas in a graph you have these relations between different components, and then you want to find out some interesting insights from that relational data. So the relationships between two nodes are represented as an edge. So the relationship can be friendship, acquaintanceship, or maybe co-authorship in a like you are together co-authored a paper. So now if when you model this relationship using graphs, then you can analyze them using tools from graph theory. So here is some history of this social network analysis. So Spinoza developed some initial models using sociology. Then in 1937, Moreno introduced sociometry, and he also invented the sociogram. Then in 1948, Bavelas founded the group Networks Laboratory in MIT, and he also defined some notion of centrality. Then in 1949, Rappaport developed a probabilistic model of information flow, and in the 70s, the field really picked up, and new features in graph theory like more general structural model were introduced. But what really helped social network analysis was the new computational power that came up with the modern computers, and also their applications to these online social networks such as Facebook, Twitter, or the World Wide Web. And so we are able to analyze more complex relational data sets using computers, and those are large graphs compared to what we are able to analyze in earlier days. Here are some basic things about graphs. So you have a set of nodes and a set of edges, and then you define the size of this is the number of nodes of a graph, and the density is the number of tries that are present, and the amount of tries that could be present. And the in degree and out degree, suppose the graph is directed, then the in degree is the sum of connection from an actor to others, and the out degree is the sum of connections to an actor. Okay. Oh, what happened? No. Okay. No, it's coming. Okay. So in this kind of social networks, there are many measures of power and prestige that you can connect, the importance, for example. So one is the degree. So by degree, I mean the total number of nodes with which a particular node is connected. Then there are other measures of centrality measures that you can think about, like closeness centrality, which is the distance of one actor to all the other actors in the network, and betweenness centrality, which is the number of so if you compute distances between various nodes, then how many times one particular node is between those nodes. Then you can compute some other things, like suppose in a network you have a set of people, and then how closely connected these people are. So one of the measures could be like you compute a clique among those set of nodes. So by a clique is basically a subgraph of a graph where you have so all the nodes are connected to each other, and so also you can try to find out near cliques, which are like cliques, but they may have some of the edges missing, and you can define a threshold, like how many edges should be present in that. So now we'll try to explain some of these interesting phenomena that happens in the in a social networks. So I have mentioned some of them, like small world phenomena, random graphs, and other things, and we'll go through some of them as time permits. So let me start with a motivating example called the Kevin-Bacon game. So this was invented by Albright, and it was to play by college students. So here basically, so you have the underlying network is the set of movie actors that have acted, say, in Hollywood films. Okay, and then so the nodes of this graph is are the actors, and the two actors are so there is an age between two actors, or there is a relationship if those two actors have acted together in a movie. Okay, so now the goal is to given an actor, you want to connect that particular actor to this actor Kevin-Bacon, so that you find what is the number of actors through which you have to pass before going to Kevin-Bacon. So there is a website called Oracle of Bacon, which uses the site Internet Movie Database to find out the shortest link between any two actors. Okay. So here is an example of that. So suppose you look at, you want to find out what is the shortest path between Amitabh Bachchan and Kevin Bacon. So here is one way to find out the shortest path. So Kevin Bacon acted with Tim Robbins in the film Mystic River. Then Tim Robbins acted with Om Puri in the movie Code 46. Om Puri acted with Rani Mukherjee in the film Yuva. And Amitabh Bachchan acted with Rani Mukherjee in the film Black. So there is a path of length 4 from Amitabh Bachchan to Kevin Bacon in this underlying network. Now the question is whether this is the shortest path. So okay, so if you put this value of Amitabh Bachchan in the oracle of Bacon side, then this will give you that, so there is actually a shorter path. So Amitabh Bachchan acted with Tobey Maguire in the film The Great Gatsby, and then Tobey Maguire acted with Kevin Bacon in this film called Beyond All Boundaries. So from Kevin Bacon to Amitabh Bachchan, there is actually a path of length 2. And this is also called the Bacon number. So now note that this particular actor Kevin Bacon is not very important. It could have been any other actor, and but this particular game was designed based on Kevin Bacon. So in some sense, you can think of that Kevin Bacon is an important node in the network, and then you want to connect other nodes to that particular node. So here is the underlying graph in this particular database. So you have about 550,000 actors, and if you compute the average path length to Kevin, so by average path length I mean you compute the shortest path from every node to this Kevin Bacon's node, and then suppose there are n nodes in the network, so you take an average by dividing all this path by n minus 1, and then that comes to be the average path length a given node has to the Kevin Bacon node. So, so it was found that the average path length to Kevin Bacon was 2.79. That means the network is not very, I mean probably the diameter of the network is not very large. You have short paths from every node to Kevin Bacon, because on average the average path length is only 2.79. So actors closest to the, but the interesting thing was that actor closest to the center was Rod Steiger, and rank of covenant closeness to the center is actually 876. So, and most actors are within actually 3 links of each other.
What is center? How are you calculating center?
Okay, so center, so that's a, so center in a graph, there are various measures of centrality, right? So based on importance of that, and then so one of the centrality could be like degree centrality. Like if you have a particular vertex, you compute the number of edges incident to it. So generally what happens is that if you are connected to many people, you are important in some way, right? So
The node with the maximum integrity can be considered as center. You are talking about like that.
so that is one measure of centrality. That's called degree centrality. So there are other measures of centrality like closeness centrality or betweenness centrality. So you can based on the particular centrality measure that you are choosing, you can define what is the central node. So there is no one definition of centrality. Based on the function that you are taking, objective function, you can have different central nodes. Okay. Okay. So similarly, for so there are similar things called ERDOS numbers. I don't know, maybe many of you who are in academics, they are familiar with this thing called ERDOS number. So it is like similar to the Bacon number, but it is for researchers. So what happens in the case of ERDOS number is that so the nodes of this graph are the researchers or the authors, and then two nodes have an edge between them if and only if they have written a paper together in some journal or conferences. So that is how these nodes are connected. So So the thing is that why was ERDOS was considered one of the most prolific, he's actually the most prolific mathematician in history in terms of writing number of papers. So ERDOS wrote more than 15,000 papers in his lifetime. Sorry, 1,500 papers in his lifetime. And he has actually wrote more number of published papers with, than anybody else. And also he had a large number of collaborators, like 507 co-authors. So he used to like to collaborate a lot. So there is this ERDOS number project that is maintained, and here you can find out which people have ERDOS number what. So let me define what is a ERDOS number. So ERDOS number is Paul ERDOS has ERDOS number 0 because he is the node, and then if you have co-authored a paper with ERDOS, then you have an ERDOS number 1. If you have co-authored with a person with ERDOS number 1, then your ERDOS number is 2. And in general, if you have written a paper with ERDOS number with a person with ERDOS number k, then your ERDOS number is k plus 1. So that is how it is defined recursively. Okay. So here also you can compute in this kind of collaboration network what are the path lengths. Average path length between mathematicians. So in this network, it was found that the average is about 4.65 and maximum is 13. So actually the diameter of this graph is 13.
There can be distant sets separate between the distant.
You are saying disconnected components, right? Yeah, it's possible that there can be disconnected components.
What is the ERDOS number in case 2? I mean, someone there are two distant sets.
No, if you are in a disconnected component, you are not in the same connected component as the ERDOS is, then the distance will be infinity, right?
The position will be invalid because there is no link between the two sets.
Exactly. So if you are in the same connected component, then only can you talk about paths between that, right? If you are in a disconnected component, then there is no path between those two, right? Okay. So you can compute your ERDOS number also. For example, my ERDOS number is 3 via a path from Paul ERDOS to SB Rao to Sushmita Ruich to me. So this is the shortest path I found till now. There may be other paths possible, but note that at this point you cannot have ERDOS number 1 because ERDOS has already died, but you can have ERDOS number 2, it's quite possible, right?
So how do you get the ERDOS number 3? You write a paper with Sushmita?
SB Rao, and then SB Rao wrote a paper with Paul ERDOS. Yeah. So I have other length 4 paths also, but yeah, this is the shortest. Okay. So this leads to an interesting phenomena of like suppose you have a large networks, with lot of nodes, and then you want to find out what is the average length in such average path length in such kind of networks. So this leads to this was initiated by a famous Harvard psychologist called Stanley Milgram. So what he did was the following: he chose random people from Nebraska. And then he told them to send a letter to a particular stockbroker in Boston, which they don't know directly. Okay, but they can forward this to intermediate people, right? But they have to know them on a first name basis. For example, if I am your close connection, then I can deliver that letter to you, and then you can deliver that letter to a particular particular person in your connection, and so on. And then you have to somehow deliver this thing to the ultimate stockbroker in Boston. So the interesting thing was, so now think of this is a very difficult problem, like because you don't, you are a node in this particular graph, but you don't have no understanding of what is the structure of the whole graph, right? And then how do you find out that whom should I deliver to? Because if you had the graph in front of you, you probably can compute the shortest path. Now you only know your immediate connection. So you know basically what are your neighbors are. You don't know the structure of the whole graph. So how do you even forward this thing? But surprisingly, it was found most of the time people were able to deliver this the letters to the stockbroker, and not only that, they could deliver it through a short path. Like in most of the cases, the average number of intermediate note that were people that they sent it before it was finally delivered was 6. So from this, this notion of 6 degrees of separation came. So though so here what is the number of nodes in this? Is potentially all the people in the United States, right? So which at that time was about I think about 200 million. So but in a 200 million node, 200 million graph, sorry, in a graph with 200 million nodes, so you can only use 6 people to send it to your final destination is a remarkable thing, right? So to put it in a more mathematical way, suppose you have a graph with n nodes, and then you want to find a path of short length which are not even dependent on n. It's not even order n or order log n, but probably a constant, right? In this case, it's 6. So that was a remarkable finding. So, and from there, so there was a movie also that was made called 6 Degrees of Separation, and there are also a very nice book on that by Duncan Watts. Okay. Any questions on that? So of course there are interesting mathematics behind that, but I will not be able to go to the explain that kind of thing. But maybe I can give you some pointers to that, why this kind of phenomena happens, that in a large graph you can have short paths. Okay. So let me tell you a little bit about the random graphs. So random graphs were basically stochastic processes defined on this graph, and then you want to find out some interesting properties which will typically occur in these real networks. So one of the first random graph model was defined way back in 1959 by ERDOS and Renyi. So their model was very simple, and it is the following. So you have a fixed set of nodes, say n nodes, and then you have a pair of nodes has probability p of being connected so independently with each other. For example, you take these nodes with 12 nodes, and suppose the two nodes, say two nodes are V1 and V2, then the edge between V1 and V2 will occur with probability P. So say, for example, P is in this case 0.1. So that particular edge will appear with probability 0.1, and this will happen independently for each particular pair you take, and then the probability with 0.1, that particular edge will appear. Now, and then you repeat this experiment for all possible pairs, and then a certain graph will form, right? Now note that this is not a, so this particular model is called the GNP model, and note that this is not one graph that you are forming. So there may be this is a family of graphs that you create, because if you do this experiment a second time with the same value of n and p, you will get a different graph. So it is not a one graph; it's a family of graphs. Okay. Now basically people like mathematicians are interested to know what are the things, what are the interesting things that can happen. For example, what is the average degree of such a random graph, or what is the average path length of such a graph, right? So okay, so what is the motivation for why am I telling these random graphs? Because suppose we want to analyze this phenomena of 6 degrees of separation using random graphs. So in particular Erdos-Renyi random graphs. So you can probably ask questions like, what will be the diameter of this graph, right? Diameter means what is the maximum possible path length in a graph, right? So it turns out that the maximum path length of the largest cluster in a Erdos-Renyi graph is it's not constant. Okay. 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 Okay, let me skip some of these details. So basically the finding is that suppose connections between people can be modeled as a random graph in the Erdos graph sense, then the average person knows more than one person, and then if we live in a small world, means within a few links, and that is say that the number of such links is constant, then the average path length should be this given by this particular expression. But then in a real network that is not the case. So in a real network what happens is that you have so we saw that in a graph of length say 200 million, only 6 connections are sufficient to reach from a particular node. So that means that Erdos graph cannot explain this particular phenomena. Okay, so yeah, so basically before you try to understand what is how you can explain this, you have to also understand in perspective what are the attempts that were made to explain that phenomena. In this case you can see that this is a very important family of random graphs, and then they are not able to explain this kind of phenomena. Okay, so then the fundamental question is, what is different between the this Erdos random graphs and the real social network? So in a random Erdos random graph, the probability between the fundamental assumption that an edge between two nodes that have a probability p independent of each other, that particular assumption is not true in a real social network. So what happens is that if you observe a social network, what happens is that there are very few nodes of very high degree, means they have a lot of connections, and there are many nodes which have very few connections. So they are not uniformly distributed. So whereas what happens in a Erdos network is that the average degree of every node is the same, because if you think a little carefully, from each node's perspective, the number of edges that are incident is same, whether you look at a particular this node or that node. But that is not true in a real network. In a real social network, you will see that there are many people who have accumulated a lot of connections. There are very few people that have accumulated a lot of connections. These you can generally, typically, these are called politician nodes. And then there are many other nodes which have very few connections, like typically 1 or 2, right? So in a more technical term, the expected degree of a particular node is not the same in a real network, right? So, and then we can see that this Erdos network is not able to explain this kind of phenomena. So let me tell you what is different between one of the fundamental difference between the Erdos random graphs and the real random graphs. So what happens is that if you look at a degree distribution, so by degree distribution I mean you plot a curve where you have the degree as on the x-axis and the number of edges with the degree k as the y-axis. And then if you look at that particular distribution, it turns out to be a normal distribution, and it can be actually proved. But in a real network, so that means that in a real network what happens is that there are some edges, there are some nodes which have very high degrees. Okay, in a normal distribution, what happens is that if you have nodes with very high degree, their probability is exponentially small, which is basically almost close to 0. Whereas in a real network, the nodes which have very high degree, they still have some finite chance of being there. And in a more technical term, they are actually proportional to the generally these are called the power law distribution, where it is like if you have a degree k, it is proportional to say 1 by k square or 1 by k pool. So they have a good chance of still surviving. Whereas in a normal distribution, it would have been like decaying as e to the power 1 by e to the power k. So the chances are very small that if you have a particular node with degree k. So any questions? So these are also generally called, as his Professor Chandan Mohinder said, the rich get richer phenomena. So here this kind of rich get richer phenomena is into play. And most of the real network have this rich get richer phenomena. Yeah, sorry.
One thing my observation in social network or in any kind of social network, there is cluster, but in your random graph there is no such cluster. I'm talking about cluster. If you consider the social network, you may find some clusters, but in random graph you may not find some cluster.
Yeah, that is true. That is true.
That's the main difference between a social network graph and a random graph.
Yes.
Clustering is the main point.
Exactly.
That's what he said about the degree. Degree clusters will have higher degree. That's what he said. Degree
Central node will have high degree. That is a cluster.
Yeah. So the ERDOS linear algorithm is one stochastic model to explain this kind of phenomena, right? And so this is actually, there is another model. So that model, you can see that cannot explain the phenomena of these large clusters. So, and also it cannot either explain this kind of degree distributions also. So that means so you have to, so as Professor Bimal Roy and Professor Chandan Mohinder said, right, you have to understand how this underlying data is being generated, right? So clearly generating edges between two nodes uniformly at random with same probability does not give rise to does not model the reality, right? So some other model is required. That model is too simplistic. That is useful for other things, but not for this kind of analyzing the social networks. Okay. Okay. So let me explain this thing. So this is a very famous model introduced by Rekha Albert and Laszlo Barabasi. This is called the preferential attachment model to explain this kind of power law phenomena. So basically what happens is that in this kind of model what happens is if you have a particular node which have lot of connections to them, then so if you have another node that is coming to the system, so the probability that this particular node is getting connected to this is actually proportional to what it has already got, the neighbors. So let me explain this in a more simple term. Suppose a person has say 100 friends versus a person has only 1 or 2 friends. So typically these are like the celebrities, right? And then suppose you want to follow in a Twitter or a Facebook. So suppose you are new to the Twitter or Facebook, you want to connect with that person who has lot of connections versus you don't want to connect probably to a person which has only 1 or 2 connections, right? So the more that you have already acquired, that more number of connections you are already acquired, that helps you to getting new connections. So that is called actually one of the manifestation of the rich get richer phenomena. Okay. How much time do I have? Okay. 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 So, but this power law phenomena, it is not. So this has a very rich history, and it actually originated even before social network graphs. So in English there is this simple law called the Zipf's law, which kind of explains the frequency of words in a particular corpus. For example, in the English, the number. So frequency of a kth most frequent, k plus most frequent word, that can be considered it is inversely proportional to that rank. So this is one of the first instance where this rich get richer phenomena actually came in the Zipf's law in the context of a language corpus, for example in English language. Okay, let me skip this thing. Okay, so another interesting thing that needs to be thought about is that suppose you are so you are part of a this kind of small world network, and then you want to find out. So you don't have access to the all the network, but you want to find out from a given node. I want to reach a particular node. So one part is that knowing that you have a small path to that, but you actually have to find out what is the actual path to that, right? Without knowing the network. So how will you do that? So this is called the decentralized search problem, and then. So if in this case the model is that you have a you only have local access to the network, means you only know your particular neighborhood, and then from the neighborhood they knows their neighborhood. So as you go to a particular node, then only your network structure is revealed. And in this kind of model, how do you find out your path in the network, right? So there are interesting algorithms for doing this kind of things. And so the important measure is that you want to find out what is the average path length that you will find from a given node to a particular node. So Kleinberg did this particular experiment where with the lattice network. So a lattice network is particular. Think of this as a two-dimensional grid. In a two-dimensional, this is a grid, and then he also connected the last two nodes on that in a circular way. And in this kind of lattice network, he found that you can find out there are algorithms which you can find out this kind of small paths to a particular given node. So basically, I am talking about the kind of 6 degrees of separation where you have to find a from a given node to a particular node. Okay. Okay. Okay, let me skip some of this. Okay. So let me explain some of the other problems in social network analysis. So one interesting problem is called link prediction. So in a link prediction problem, what happens is that suppose you have a particular set of nodes, and then you want to predict what are the friends that you should suggest. So for example, if you go to the to a particular Facebook or LinkedIn, then you see that so they suggest that you are probably also connected to that particular node, right? So how do you do prediction of these things? So this problem is called the link prediction problem, and one of the way that you can do the link prediction is the following. Like you can find out, so for a given node, you can find out, so between two nodes, so what are the common neighbors that they have, common friends that they have, and based on that you can do the prediction for that. Then there are other kind of problems like the community detection problem, where you want to cluster this particular set of nodes into communities and find out what are the friends that are close together in the network. Okay. Okay. So in summary, a network is considered to be a small world phenomena if its diameter is approximately the logarithm of its size, and most uniformly random networks don't exhibit small world phenomena. And that the network exhibits small world phenomena doesn't mean that it can be navigated in the order log n time. Okay. And here are some textbooks that you can read to understand more about these problems. Okay. Thank you.